Excellent. Quick, and Palmdale. Okay, so y'all are actually neighbors there. And I used to go back and forth between those two places all the time. Just by way of a little background, we have 3 different aircraft design instructors here, and they all do things differently. Professor Helbling always does a design, build, test operation. They can do ground tests, but they can flight test on a launcher basis. Professor Ashworth always does a paper study followed by a wind tunnel model. That's what these 2 groups are going to be doing today. My groups have a choice. The requirements for these projects were provided to the students by Professor Ashworth, if I'm not mistaken. He gave them a requirements document, and they've been working to that. And this is the end of the first semester of a 2-semester sequence, so they're only halfway through the whole project. In nominal terms, we're actually trying to get them to the end of the preliminary design phase at this point, and getting them ready to go into the detailed design phase starting in January. So that's where they are doing these projects. They will do more than introduce themselves and their teams and their topics. We have some, Mr. Ashworth has 3 teams, if I'm not mistaken. And how many are we going to be here this morning? All 3 of them? All 3. All 3 will be going one after the other? Yes, sir. And so there'll be a 10-minute break between each one. And off we go, unless y'all have something to add. Sure, they're nice in their team shirts. Turn it over to the team leader, and I'm going to give you all some in just a second.
All right. Okay,
open. Mr. Ashworth.
So loud enough for everyone here. Are we ready?
We are.
Okay. My name is Kyle Hansen. I am the team lead of Launch Tech, and today we're going to give our presentation on the preliminary design of our aircraft, the PT-1. And during this presentation, we're going to refer to the upper screen as the primary screen, and this screen over here is going to be the secondary screen. So first, I'm going to introduce you to the members of Launch Tech. We have myself, Derek DeVries at the computer, Nathan Davis, Daniel Schreier, Michael Peterson, Chris Hansen, and Kasim Hashim, and their respective duties are on both screens. So first, an overview of what we're going to cover today. I'm going to start you off with an introduction to the PT-1, and then we're going to go through the mission specs and the profile, and then the preview, the description of the PT-1, some individual component designs, and then the analysis, a cost estimate, and the conclusions and recommendations from this preliminary design. So first, an introduction to the PT-1. So what is the PT-1? It is the first stage in a 2-stage to orbit vehicle, sometimes referred to as an air launch vehicle. What that means is it's a large fixed-wing jet aircraft that is designed to carry a second stage space vehicle up to altitude where they separate, and then the second stage delivers a small payload into low Earth orbit. In the case of the PT-1, it is specifically designed to carry the Ambassador, which is being designed by Genesis, who is going to present immediately after us. And an important thing to know about the Ambassador is it is fully reusable, which means that after it delivers its payload, it's going to re-enter the atmosphere and land on a conventional runway. So why is this being designed? So first, the current launch options just aren't adequate for small payloads. They're optimized for very large payloads. An example of this is on the primary screen. That's the Spacex Falcon 9. Its mission price is $61.2 million, and it can carry 29,000 pounds in the low Earth orbit. And on the secondary screen is the H-2A rocket, a mission price of $97 million, and it can carry 26,000 pounds in low Earth orbit. So these are optimized for very large payloads, and they're just not practical if you're only looking to launch, say, a 1,000-pound payload or much less. And so these small payloads are still getting to orbit currently, but what they currently have to do is piggyback off of these larger payloads on these large current launch platforms. And they do that as what's called a secondary payload. So what that means is they're basically at the mercy of the primary payload. They're just paying for a spot on the rocket. So they're limited to the orbit of the primary payload. And this is not ideal for the small payloads. An example of this can be seen on the secondary screen. This is a small demonstration satellite number 4. It was a 220-pound payload, and it was launched on an H-2A rocket as a secondary payload to the DCOM satellite. And this is not just one case. This is a market that's really expanding. At the AIAA Small Sat Conference in 2014, SpaceWorks Enterprises, they presented that 92 small satellites were launched into low Earth orbit in 2013. They expect this number to increase to up to 540 by 2020. So it's over a 400% increase in just 7 years. So that's a market that's really expanding. And this is a market that the PT-1 Ambassador are going to get into. So we're going to give these small payloads the opportunity to be the primary payload, giving them the orbit option that they want, their launch date, and because the Ambassador is fully reusable, we're going to have the lowest mission price on the market. So we have a mission price of estimated to be $8 million. We're able to achieve this because with the reusable second stage and with the two-stage to orbit platform, we have less fuel, we have a lower manufacturing cost per mission because we do not have to manufacture that second stage for every launch. So that's the PT-1. And now Derek DeVries is going to present the mission specs and profiles of similar aircraft and then a description of the PT-1.
Thank you, Rob. So the mission specification are shown here on the primary screen. This was developed by NASA and the DoD because they recognized the need for the capability of sending small payloads into low Earth orbit. Next slide. On the primary screen, you can see a general description of our mission profile. And on the secondary screen, you can see a description of each individual phase. Essentially, the PT-1 mated with the Ambassador will take off from a conventional 10,000-foot runway and climb up to 60,000 feet. Well, the two vehicles will separate. The PT-1 will return and land, and the Ambassador will go up to low Earth orbit and deliver its payload, and then re-enter the Earth's atmosphere and land. Now I'll discuss similar aircraft. During the design process, we looked at several other two-stage launch vehicles that are currently on the market. One example of this is the Orbital Atk Stargazer. The Orbital Atk Stargazer is capable of taking a 40,000-pound payload up to 40,000 feet with an approximated mission cost between $15 and $25 million. PT-1 is capable of carrying 75,000 pounds to 60,000 feet for a mission price of $8 million. Another vehicle we examined was the Virgin Galactic's White Knight II, excuse me, which has a payload of 37,000 pounds and a separation altitude of 50,000 feet. Additionally, its mission cost is $10 million. The PT-1 is still capable of beating the White Knight II in all of these categories. During the design process, we also looked at the Boeing B-52 Stratofortress. This is not a two-stage launch vehicle, it is a heavy bomber. However, during the design phase, we noticed similar features coming up between our vehicle and the B-52. This was due to some similarities in both weight of our payload and its maximum altitude. Now I'll go over the free view and the PT-1 description. For the PT-1, we decided to go with a single fuselage design. Due to the size and weight of the Ambassador, we attempted to make a dual fuselage design, but we could not keep the engines above the runway. So we maintained the single fuselage design and designed from there. The Ambassador is also designed to fit underneath the PT-1 in a bay that we have designed. The wing has a planform area of 7,040 feet squared, and it is high mounted. We've also designed winglets in order to improve the effective aspect ratio on the plane. The PT-1 is also designed to use 4 GE90 115B engines. These are the largest commercially available engines on the market, and these engines will provide the necessary thrust that we need at altitude in order to perform our mission. These engines are also located underneath our wing, as you can see from our isometric view on the secondary screen. For the empennage, we went with a conventional tail design, with the horizontal tail being level with our wing. And for the landing gear, we went with a quad landing gear layout, similar to the B-52, except our rear landing gear is spaced wider in order to address tip-over criteria. On the primary screen, you can see the free view that is generated for the PT-1 and some overall dimensions. Some of the overall dimensions that exist are the length of the fuselage being 205 feet. Excuse me. Next slide. And now I'll discuss the layout and design of the cockpit. For our cockpit, we designed the cockpit around having 2 average-sized pilots. We approximated the spacing and sizing of the controls based on the Roski text for ease of use for the pilot. We've also incorporated a little bit of additional space in order to accommodate the pilots wearing a pressure suit, which they will have to wear at the 60,000 foot altitude. The cockpit is also designed in a modular fashion to incorporate future design for a escape capsule in order to safely get our pilots out should something go wrong. The PT-1 was required to fulfill field of view requirements as designated by the FAR 25. The field of view needs to reach 15 degrees above eye level and 15 degrees below. Additionally, there cannot be any obstruction between 30 degrees and 20 degrees from the main pilot. Also, any obstruction between 20 and 60 degrees, the obstruction can't be wider than 2.5 inches. And the full field of view needs to reach all the way to 135 degrees. PT-1 satisfies all of these requirements. And now for the fuselage design and ambassador location, Nathan Davis.
Hello, my name is Nathan Davis, and I'll be presenting fuselage design and ambassador location. If you look on the primary screen, you will see a side view of the PT-1 with the ambassador housed inside it. The PT-1 is 205 feet long, as Derek mentioned, and the bay which holds the ambassador is 75 feet long. The ambassador itself is 65 feet long and sits in the middle of the bay, giving approximately 5 feet of clearance longitudinally on either side. And now if you look at the primary screen again, you will see a front view and a rear view of the PT-1 with the ambassador. The PT-1's diameter is 22.9 feet, and the bay which holds the ambassador is 18.3 feet wide. The ambassador itself is 17.1 feet, giving approximately 1.1 feet of clearance on either side of the ambassador. And the ambassador's height is 9.3 feet. Now if you look on the primary screen, you'll see the ambassador in its extended position. And if you look on the secondary screen, you'll see the ambassador in its normal position. This process will extend the ambassador using a scissor lift before separation. This is to prevent the ambassador from hitting the fuselage as it separates. After this process, after separation is complete, the scissor lifts will retract and several panels will slide into place, effectively closing the fuselage and preventing unwanted airflow from entering. And now Daniel Schreier will present the layout and design of the wing.
Thank you, Nathan. PT-1's wing is designed to take the PT-1 up to 60,000 feet and fly at 0.75 Mach. To achieve this, it has a wingspan of 251.7 feet, a quarter chord sweep of 15 degrees, and a taper ratio of 0.4. Additionally, on the end of the wingtips are winglets. I'll go into more detail about the winglets on the next slide. On the secondary screen, you can see a plan form drawing of the wing that we have it set up. Now for winglets, according to Raymer, winglets can increase our effective aspect ratio by up to 20%. We estimate that we can achieve 15% using winglets modeled after current designs. For example, on the secondary screen, the PT-1's winglet versus the Aviation Partners split scimitar winglet. This is a new winglet designed recently by Aviation Partners for 737s, and it increases the performance of the wing by reducing drag significantly versus a wing that does not have any winglets at all. Now on the primary screen is our CL alpha plot of the airfoil and the wing. Our airfoil data we retrieved from NACA data, and it's from report 824. Our airfoil we chose is a 63-412. It's a common transport airfoil. And we use methods from Brandt, Raymer, and Roscoe to convert from the airfoil to a wing. Now on the primary screen again, our flap configurations. The lowest configuration is our clean configuration, followed by takeoff and landing sequentially upward. For our takeoff performance, as you can see on the secondary screen, we have 20 degrees of flaps for takeoff and 25 degrees of flaps for landing. These are slotted flaps that take up 51% of the wing and 30% of the chord. We use methods from Raymer and Roscom to verify the performance of these flaps. Now the VN diagram. First, I'd like to clarify the Q limit that we have shown. The Q limit for 20,000 feet is beyond Mach 1. And because the PT-1 is a subsonic aircraft that has turbofan engines, we cannot attain the Q limit as shown. The Q limit as shown is the same Q limit from sea level that would get to the same Q. Therefore, it exceeds Mach 1 when going to 20,000 feet. Additionally, on the plot are the stall lines plotted for sea level, 20, 40, and 60,000 feet. Our N max limit is 2.16, and the minimum is the CFR requirement of -1. And now Michael Peterson will present the propulsion system.
Thank you, Daniel. For the PT-1, shown on the primary slide are the possible engines for the PT-1. Of these, the G90-115B engine was chosen. This engine has a proven altitude of 43,000 feet. However, it is similar to the Pratt & Whitney 4098, which has been proven to 60,000 feet and chosen for the Stratosphere project. In comparison to this engine, the G90-115B has a higher continuous thrust and higher pressurization ability. This engine also has been proven up to 0.83 Mach. However, the thrust requirement for the PT-1 is 60,000 feet. It was the lightest configuration to choose 4 of these engines. Shown on the primary slide is the thrust available versus thrust required for sea level and 30,000 feet. The current plan is for the PT-1 to take off with 2 engines and air start the remaining 2 at 30,000 feet due to the excess of thrust available at these altitudes. And shown on the primary slide is the thrust available for thrust required for 60,000 feet. At this altitude, the PT-1 is planned to fly at 0.75 Mach, and it's capable of flying between 0.66 Mach and 0.9 Mach when the engines are not able to, or chosen as the max speed, as the engines are unlikely to perform past this speed. For these thrust required, or thrust available, an estimated of 7.8% losses due to mechanical and other losses was chosen, or estimated, with an inlet efficiency of 98%. Thrust required was given a conservative estimate due to the likelihood of under-predicting drag and the effects of the ambassador on the total drag when releasing into the airflow. Shown on the primary scene is the excess power plot. Red dot is the chosen power, or the chosen cruise plot for the PT-1. This meets the 500 foot per minute FAR requirement for jet transports at 0.75 Mach at 60,000 feet. PT-1 has a max altitude of roughly 64,000 feet, and for the excess power, maximum speed was roughly 0.9, was chosen as 0.9 Mach for higher altitudes, as the PT-1 was unable to perform past these. For insulation, the engines were chosen to be installed underneath the wing in order to reduce bending stress from lift during flight. These also chosen to be mounted under the wing in order to reduce the amount of boundary layer interference. With the placement of the engines, these are able to fit within the 150 foot runway, as well as meeting any ground clearance criteria, which will be covered in the landing gear section. For the PT-1, the current fuel plan is to have an allowable taxi period of 15 minutes and take off within 5, climb up to 50,000 feet at 2,000 feet per minute, or due to thrust losses, slow down for 1,000 feet per minute up to 60,000 feet, cruise out at 500 nautical miles, release the ambassador, cruise back at 500 nautical miles, descend for 45 minutes with a possible loiter period of 30, with an extra 45 minutes due to power requirements for reserve fuel, and land within 5 minutes. This gives a total fuel weight of 68,000 pounds, although the PT-1 is budgeted for 70,000 pounds in case any errors are made during flight. Shown on the secondary screen is where the fuel tanks are stored. Due to the large amount of area, or large amount of volume within the wing, this fuel is recommended to be within the 50 and 75% spars. Now we're going over the layout and design of the landing gear. Landing gear system is a retractable system to reduce drag at the cruise altitude. These are chosen in quadricycle configuration to accommodate the heavy weight of the PT-1 as well as allow easy access to the payload area when mounting the ambassador. For typical criteria, the angle between the most rear CG and the rear gear is estimated at least 15 degrees. PT-1 is 71 degrees, which prevents the PT-1 from being able to rotate during flight or during takeoff. However, due to the design of the PT-1 is able to conduct a rotationless takeoff. For typical angle, in the lateral direction, the angle between the ZCG and the line between the front and the rear gear needs to be at least 55 degrees. Shown on the secondary screen is the current model, estimating points in space for ZCG in both gear. This is, for tip over, this needs to be at least under 55 degrees, and currently it is 54.8. This is achieved by placing the rear gear and pod and landing gear outside the fuselage of the aircraft. For ground clearance, the angle between the rear CG and the bottom part, or the rear part of the plane is recommended at least 15 degrees. The PT-1 currently meets this at 15.02, preventing it from touching or the tail from scraping the ground during any landing procedures. In the lateral direction, ground clearance between the most outboard gear and the bottom part of the plane needs to be at least 5 degrees. Currently, this is met with the winglets being in the critical condition at 6.27 degrees. For tires, these are sized with the critical loading condition for 54 by 21 with a rated load of 68.5. As the rear tires experience a static and dynamic loading of roughly 66.6 thousand pounds, these meet the rated loading for the tires. Versus the front gear are estimated to take 40% of the total weight, 20% for strut, and 10% for tire. So all gear have the same dimensions and tires. Shock absorption, all your struts are chosen. The total length of 9.5 for both the rear and front gear. Total diameter of roughly 1 foot. Brakes are added both on the front and rear gear in order to slow down the PT-1 during landing. Both of these gears are roughly estimated for 7.6 thousand pounds per set in order to accommodate the heavy loading on the gears during landing. The gear is supposed to be designed to be stored within the fuselage. The front gear are meant to be tracked within the cockpit area, while the rear gear are designed to be able to fold inwards from the fuel pods, or the pods that they are stored in, inwards towards the fuselage. Now, presenting stability control analysis.
Thank you, Michael. All right, so the horizontal stabilizer was sized using X-Plots. Typical jet transports have a static margin between 15 and 25%. The PT-1 has a horizontal stabilizer area of 1,600 square feet to give it a static margin of 18%. The PT-1 also has a CM alpha value of -0.9. So the vertical stabilizer was also sized using an X-plot. Jet transports typically have a value of 0.05 for CM beta, and PT-1 has a 927 square foot vertical stabilizer to give it a CN beta of 0.064. This extra CN beta helps the PT-1 during the one engine inoperable scenario, which will be covered later in this section. The PT-1 has both a high wing and leading edge sweep, which help it with its roll stability. The PT-1 has a CL beta of -0.036. So on the secondary screen, you can see a CM versus alpha body axis plot. PT-1 can be trimmed at 60,000 feet at 0.75 Mach without stalling either the wing or the horizontal stabilizer. The horizontal stabilizer is variable incidence and has an incidence of -3.1 degrees during trim. So for the one engine inoperable scenario, the PT-1 takes off with 2 engines. If the PT-1 was to lose one of these engines, it would have a rudder deflection of -0.07 degrees and a corresponding aileron deflection of -2.5 degrees. This small rudder deflection is typical of jet transports with a large CN beta due to the fact that the CN beta is typically for a 2-engine inoperable scenario. The PT-1 can land in a 28.3 foot per second crosswind. This analysis was done using equations from Yekout. Both Yekout and Raymer, Yekout and Napolitano recommend a maximum rudder deflection of 25 degrees. We chose 20 degrees to make a conservative estimate, and this gave a corresponding rudder deflection of 3.38 degrees. And now I will present the layout and design of the empennage. So the horizontal stabilizer, we are using a NACA 0012 symmetric airfoil. It is variable incidence with a full span rudder at 30% of the chord. The vertical stabilizer, we are using the same 0012 symmetrical NACA airfoil. And we have a full span rudder at 30% of the chord. And now Nathan Davis will present structural layout and construction.
Hello again, my name is Nathan Davis and I'll be presenting structural layout and construction. Now we'll start with the fuselage structure. The skin of the fuselage is 1/8 of an inch thick and is made of a high-strength graphite epoxy. And the stringers of the fuselage, there are 133 stringers along its circumference, with the stringers near the bottom having greater areas to deal with the extra stress. The stringers are also made of a graphite epoxy. The fuselage's ribs are spaced 10 feet apart and are made of a 70-75 T6 aluminum. There are 20 ribs along the fuselage's length. The wing has 1/8 of an inch thick skin and is also made of graphite epoxy. This is with the exception of the area around the leading edge of the wing. This is due to having high temperatures along the leading edge of the wing, and so the area around the leading edge will be made of a 70-75 T6 aluminum. The stringers in the wing total to an area of 278 inches squared and are also made of graphite epoxy. The wing spars occur, we have 3 spars, they occur at 25%, 47.7%, and 70% of the wing. These spars are made of 70-75 T6 aluminum and come together to form the wing's wing box. There are fuel tanks between the second and third of these spars. The PT-1 has 126 ribs along its wingspan, and each of these ribs is made of 70-75 T6 aluminum and has false ribs in between each of the real ones. The false ribs occur halfway in between each one, and a false rib is a rib that consists only of the leading edge portion of the rib and is there to prevent the deformation of the leading edge of the wing. Our horizontal tail structure, we also have 1/8 of an inch thick skin here. It is also made of graphite epoxy with the exception of the leading edge due to the high temperatures. The stringers here total to an area of 32 inches squared, and the stringers are also made of graphite epoxy. The spars here occur at 25%, 50%, and 70% of the wing, or 70% of the horizontal tail, excuse me. And the last spar also serves as the attachment point for the PT-1's elevators. These spars are made of graphite epoxy this time around. The ribs are spaced 24 inches apart, and there are 40 ribs along the horizontal tail. There are also false ribs in the horizontal tail spaced halfway between each real ribs. The ribs are made of graphite epoxy as well. Back on, there you go. The skin of the vertical tail is made of graphite epoxy with the exception of the leading edge, and the stringers total to 30 inches squared and are also made of graphite epoxy. And the spars in the vertical tail also occur at 25%, 50%, and 70% of the chord. They're made of graphite epoxy, and the 70% spar serves as the attachment point for the PT-1's rudder. The ribs are spaced 24 inches apart. There's a total of 20 ribs along the span of the vertical tail. There are also false ribs halfway in between each real rib. The ribs are made of graphite epoxy as well. And now Kasim Hashim will present weight and balance.
Thanks, Nathan. I'm Cassie Machine. I'm going to present the weight and balance analysis for our freedom design for the PT1. So in the secondary screen, you see component weights for the PT1, including the CG location within the fuselage station and the waterline stations. At the beginning of our designs, we estimated the component weight by using Roscom weight fraction method, which is a fraction of the takeoff weight. And then we have done structural analysis which increase the structure weight so that the wing structure is 55,000 pounds, the fuselage weight is 25,000 pounds, the empennage is 7,600 pounds. For the fuel tank capacity for the PT1 can hold 70,000 pounds, and the payload, which is given from the RFP, is 70,000 pounds. On the secondary screen, you see fixed equipment that existed on the PT1, including the retraction system of the Ambassador. The choosing of those components based on the mission and the type of the PT1, calculating those weights used by Roscom method. So we came up with a total weight of 34,000 pounds, and the CG locations of the fixed equipment is 973 inches within the fuselage station. For the power plant breakdowns, as mentioned previously, PT1 used four jet engines. The total weight for the power plant is 74,000 pounds, and this weight distributed into the subsystem, as you see in the main screen, so that the engines have around 85% of the weight, and the remaining weights go to the other subsystem. The overall CG for the power plant is 935 inches within the fuselage station. In the main screen, you see a different weight scenario, including the takeoff weight, and after takeoff weight with a 60% fuel burn, and after we drop the Ambassador. The takeoff weight is 362,000 pounds, and between that and after we drop the payload, there's only CG, 6 inches of CG movement to the back, which is good for stability analysis. On the secondary screen, in the secondary screen, you see locations of the CG within the waterline station. At takeoff, it's 196 inches, and on this wing buttock lines, there's no CG locations because of the symmetric of the component around that axis. The main screen shows side view drawing. The horizontal axis represents the fuselage station. The vertical axis represents the waterline station. The diagram includes the component CG location, including the takeoff CG. And the takeoff CG is located right after or in front of the wing CG and closer to the rear wing landing gear. For the excursion diagram, it shows the relation between the CG and the weight, and it also shows the most half and the most forward CG locations during our mission. The excursion diagram lines start from the smaller weight, which is in this case the empty weight, and as we added weight, the lines go to the next point. So in that case, the lines go to the added fuel, and then it goes to the takeoff weight. That's when we add payload, and then to the next two scenario, which is when we burn 60% fuel and after we drop the payload. Now Daniel Schreier will continue with the drag results.
Thank you. On the primary screen, you can see our drag puller. This was developed with a method from Roscom, and we used the wetted area from our CATIA model to come up with the plot. The plot goes from our clean configuration with the lowest drag to our most dirty configuration at the top with landing gear deployed and flaps deployed for landing. Now the verification of the performance characteristics. On the primary screen, Our requirement is to achieve 60,000 feet. This is our most important requirement. For 60,000 feet flight, we first analyzed our wing and verified that it could achieve this altitude and hold the PT-1 there. Additionally, from our stability and control analysis, we verified that we could trim the aircraft at 60,000 feet. And from our excess power plots, we determined that the PT-1 has an excess of power and can maintain this altitude. On the secondary screen, our takeoff and landing verification. The PT-1 is required to take off and land within a 10,000-foot runway. And to reiterate again, the PT-1 does not rotate on takeoff. It deploys flaps at 20 degrees and has an incidence of 3 degrees. Our analysis used this when using the Raymer method to determine our distances required for takeoff and landing. And now Kyle Hansen will cover the cost breakdown.
So once again, my name is Kyle Hansen. I'm the team lead of Launch Tech, and I'm going to wrap up the presentation with a cost analysis, a labor cost and breakdown, and then some conclusions and recommendations from the preliminary design of the PT-1. So the cost analysis in the RFP stated that we were required to be cost effective for a 3-unit purchase. So in order to do this, we wanted to determine how many missions it would take to break even on the cost of a PT-1 and ambassador system. So we worked closely with Genesis to determine an overall program cost for the PT-1 and the ambassador. For the PT-1, we did it using the DAPCA4 cost analysis model, which was developed by the RAND Corporation, and it gave the PT-1 a program cost of about $5.4 billion, and then we combined that with the estimate from Genesis for the ambassador to get a total program cost of about $13.5 billion. So then we determined the estimated mission cost to launch one mission with the PT-1 and ambassador, and to do this we took into account fuel costs, crew costs, some estimated legal fees, and then the highest cost for the per mission is the maintenance required on the ambassador's engines. So we got to a mission cost of approximately $1.8 million. So we wanted to have the lowest mission price that we possibly could to have the most cost-effective design. So we chose a mission price of about $8 million. So this gives us a profit per mission of just over $6 million, and it's estimated that in between 720 and 730 missions, you can break even on the cost of one PT-1 ambassador launch system. And this is not an unreasonable number because, like I stated earlier, the PT-1 and ambassador are both fully reusable, so we can have multiple launches and many launches per year without having to manufacture a new ambassador. And as you can see on the secondary screen, it is our mission price compared to some of the competitors in the industry. So now a labor and cost breakdown to go over the hours that have been put into this design. So on the primary screen, you will see the total hours compared to the predicted hours for the design of the PT-1 up until this phase. The predicted hours are based on 2 hours outside of class for every 1 hour inside of class. And our total hours are 1,783 hours, and that is higher than the predicted hours of 1668, so we're putting a lot of work into this project. And we also use this to estimate the cost up into this phase, and we did that by breaking down the hours into 5 different categories and then predicting the cost per hour of each of those categories. We got to a total cost at this point of about just under $100,000. And so on the primary screen, you will see a breakdown of the hours and the different sections that they were broken down into, with engineering being our highest hours. And then on the secondary screen, you will see that the engineering cost is also the highest cost, followed by engineering management. So now some conclusions and recommendations that have come from this phase of the design. So first off, we've concluded that maintaining flight at 60,000 feet is challenging. As you've seen, the PT-1 has 4 very large engines and a very large wing, but we do have the thrust available at 60,000 feet in order to maintain flight. But we have a small range of velocities that we can fly over at this altitude. Also, the second stage retraction system is not a common system for an aircraft. So we were conservative when we estimated the thrust losses due to power generation that were required for the PT-1 in order to provide enough power for this system, but there is not a standard way to predict this sort of thrust loss. And thirdly, on the primary screen, we made conservative drag estimates for when the PT-1 is fully exposed into the airstream but still attached to the ambassador. Once again, this is an uncommon situation for a PT-1, or for an aircraft. So there's still not a standard way to analyze the effects of actually bringing it down into the airstream and how that affects the moments on the aircraft. So the combined weight of the PT-1 does meet the requirement of 500,000 pounds at takeoff between the PT-1 and the Ambassador at a total weight of 362,000 pounds approximately. We've shown that we're capable of cruising at the 60,000 foot altitude. We're capable of trimming at that altitude. We can take off and land on a 10,000 foot runway as required. And then we determine our mission range is about 1,000 nautical miles, which is 500 nautical miles out, 500 nautical miles back, giving the Ambassador a wide range of separation locations. And then our reusable second stage does indeed reduce our launch cost and our overall mission price. So recommendations coming from some of these conclusions. First, we recommend that we perform an analysis to optimize the separation speed and altitude. We are capable of meeting the requirement to fly at 60,000 feet, but it does require, like stated, the large engines and a large wing. So we just want to verify that the extra costs associated with these engines and large manufacturing and material costs of a large wing are indeed offset by the savings of taking Ambassador up to that high altitude. Also, the analysis of thrust losses due to power generation kind of goes hand in hand with the third recommendation, which is further analysis of the retraction system. Once again, we make conservative estimates for these thrust losses, but it would be important to know the exact amount of, or more approximate power necessary to run such a large mechanical system as the retraction system. And with the retraction system not being a common system, to do a further analysis of the stresses on this system and just get an overall more accurate design for the system. And then finally, we can go back to the recommendations. Finally, wind tunnel testing with the Ambassador, fully extended. So like I stated before, extending the Ambassador down into the airstream is not a common practice for an aircraft. So to be able to model that in the wind tunnel and see what kind of moments that it puts on the aircraft as we are retracting it and how that affects the transmission. So on the primary and secondary screen are some references that were used in this design and this presentation. And then I'm going to open it for questions.
Start with our distinguished guests, and then the professor has any questions. And then I'll- There's a microphone over there, so.
Two. There we go. You guys did a pretty good job there. I have a question about the payload and the engines. Mostly being if they don't work. So you have on takeoff 2 engines.
Correct.
If one of them fails, you guys can take off.
Correct.
What's your runway requirement for that?
What's our, excuse me?
Your runway length requirement for single engine takeoff?
For single engine takeoff, to be honest, do you have that number?
Currently, for takeoff, it was estimated that the engines run about.
Don't be shy.
Currently for takeoff, it was estimated that the engines are running about 47% power. So with one engine running, it can produce about enough power to maintain the same amount of takeoff.
The other question I had is the payload. Let's say you get up to altitude, you put the thing out in the airstream, you go to launch it, and it doesn't launch off. Do you guys have an emergency mechanism for ejecting it? And how does that affect your performance? Like, let's say you can't drop it out of the plane and eject it, and you have to land with it. How does that affect your performance? Did you guys look at that?
Well, we can't land with it full extended, of course, but as far as if they get fully extended and then cannot, for some reason, launch, it would be an emergency kind of, it's kind of like an explosive charge to get it to just get away from us. And we're launching from in the right around Puerto Rico, I believe, is our predicted, where we're thinking the airport's going to be. We have an airport in Puerto Rico. and Jen should present that or knows that. And so we will be over the ocean as far as throughout the whole mission. So it would be injecting the payload into the ocean.
And let's say you can't just drop it out of the plane and you have to come back and land with it. Did you guys look at those numbers?
Yeah, we can land with them still inside. We still have the capability of getting it down and getting it stopped within the 10,000 foot.
Okay.
Again, congratulations on getting through this semester.
Thank you.
And, you guys did a good job. As far as in the beginning, you have all the different, I guess, methods of ways to launch payloads and stuff. And you had a mission price of $8 million. It might, I don't know, for engineer types and people wanting to buy this, it might be good to just have a graph of showing the price comparisons where yours fits in compared to other methods and stuff. It's kind of, I don't know, something I wanted to see, but let's see. Have you guys thought about possibly a universal application of your design, catering to, I don't know, the Department of Defense or anything like that?
Do you mean like the possibility of having other second stages besides the Ambassador that we could potentially launch?
Or launching, I don't know, a missile of some sort or something like that, that could go low orbit. I don't know if it's really practical, but other marketing.
I don't know. We haven't looked into it as far as missiles that could potentially be launched from the PT-1, but I'm sure it's a design that we could look into in the future. Going by the RFP, we were focused on getting the Ambassador up there and out. Yeah.
Slide 31, Alpha. Your airfoil to wing craft.
Yes.
Okay. For that, does that take into account the assumption for the winglets that they help with the lift and stuff, or is that just straight airfoil and then straight to wing?
I'll pass the mic to our aerodynamics, Daniel.
The airfoil itself is just the regular airfoil plane. However, the wing analysis, the wing plot in the orange, doesn't take into account the extra aspect ratio from the winglet.
Does or does not?
It does.
Okay, 51 Alpha. So for stability control, I like the recommendation that you made to look into the wind tunnel analysis of having it deployed. I think that's a real good thing to look at. My concern was the sizing of the stabilizer and even your elevator. Would it be able to overcome the moment created from the deploying the Ambassador?
That is exactly what we want to look into, and that's why we did go up to a static margin of the 18% to make sure we had a considerable static margin, but that is exactly what we would like to look into and research.
Okay, and kind of the same thing with the drag analysis. You said that your dirtiest configuration was gear deployed and flaps, but really, is it your dirtiest configuration?
What we estimated, and if you can go into the drag pool, what we estimated for the performance of the power plant was a CD of 0.15. So that is essentially at our landing flap, landing gear, and a CL of 1.2, which it's stalled. So it's a higher, it's a conservative estimate for how much drag we could possibly get with the ambassador down. So it's even higher than our landing configuration is what we assumed. We assumed it would be incredibly significant, yeah.
Okay, now, last question, I'll stop bothering you.
Not bothered.
So, for your structures with the composites and the aluminum, I don't know if you thought about bonding methods and how that would go, bonding how to put it together, the metal with the composite. But aside from that, do you have any, I don't know, temperature data on the graphite epoxy? Because it gets cold at 60,000 feet. So I don't know if you considered that.
We did consider that. We worried a little more about the high heat at the leading edge, which is why we put the aluminum at the leading edge and for impact, of course. But as far as the cold, according to the research we did in Rossum and Raymer, composite do a lot better in cold than they do in heat. So we went with heat as the critical design point.
Mr. Haslam has another questions? I didn't have a copy of the slides, so I'm just going to go through in the direction
Okay.
that I took notes. I'm worried about the horizontal tail being level with the wing. You're going to get some buffet from that. You may not have moving that tail, probably off of the vertical, but you have to put it. The B-52 takeoff approach is a perfectly reasonable thing to do. You are right to be worried about the wing incidence angle and flap setting. I thought the CAD work on the forward fuselage was the best I've ever seen. Who did that?
Thank
Who
you.
did that?
You love your CAD work.
Oh, you did. That's the best blended forward fuselage I've ever seen. I wish you'd write down, just give me a bullet outline of how you did that so I can put that up at your class. Anytime you've got an airplane that has a long longitudinal cutout in the fuselage like you have, there's going to be a weight penalty associated with flexing of that fuselage. Did you account for the extra structural weight that you're going to have?
We did have the stringers at the bottom, at the edges of the ambassador bay are roughly
Well, this is one of
twice.
the things, when I look at that, I don't see the cutout. I assume that's the wing box going across the top.
Is that from behind the bay?
You're taking a gander at
Or is
the
it
empennage.
I'm very worried that you may not have modeled that correctly. That cutout, just think about it.
Would you like to cut out before the bay, so it shows the bay?
I want to see the whole structural arrangement there, because that fuselage is going to flex, I promise you. Good idea on the winglets. Is that going to be one of the things you look at in the tunnel? One of the things I would love to have seen in this presentation, you are fixing to go to detail. I would love to have seen some conceptual presentation on what your wind tunnel model is going to look like. All I was able to infer from what you said was that you were going to look at the thing with the payload up and payload down and the drag comparison. There are other aspects of this model that need to be looked at in the tunnel, especially the location of the horizontal tail, the effectiveness of those winglets. Would be nice things to know.
Okay.
At this point, what you have is what you have, and you have to make that work. I just wonder though, if a braced wing concept might not have been a little more structurally efficient weight-wise. On numerous occasions in your presentation, this one, you have tables of data. Tables are okay, barely, in a report. They're awful in a report, in a presentation. Anytime you've got a table, think about finding a way to make it a graphic. For example, who talked about flaps? Who was talking about why not just give me a planform view of the wing, and it showed me all those dimensions and areas? That would be so much more effective. Just piles of numbers like this are just gone into it on.
Okay.
Anytime you can convert a table to a graphic, you should use it.
Okay.
Never saw the drag color, even though you talked about it a lot. Never saw the K1, K2, C0, never saw this one, can't see that. The loss model was around 8% for your engine, is that right?
Mm-hmm.
Okay. And you base that on what?
Based on the various jet transport aircraft and their data. Out of Roscoe.
Class, out of
Out of
Roscoe.
Roscoe.
Out of Roscoe,
Yes,
okay. Just make sure you like that number, because it's a big driver. I also had questions about your takeoff distance, your refused takeoff. What if you have to bring the payload back? Even if you can retract it, that's going to make your weight go up. I'm not sure your landing speed accommodated that. You kept saying high temperature, if this is a subsonic airplane. I really don't know where there are going to be any high temperature problems in this operation concept. I really don't. When you're doing the structural layout, it'd be nice to see the rudder and the elevator separated from the vertical and horizontal stabilizers. I never saw any pie charts with weight fractions showing me comparisons with airplanes. Another design feature that would make this thing a little safer to operate might be outriggers. You're doing a non-rotating takeoff like the B-52 with a centrally located landing gear. You have those engine cells up there. It might not cost you too much for this outriggers. Again, the cost analysis. I'd like to know the number of missions a year. You can probably say once a week, once a month. Two airplanes, 50 use a year. I can start doing the math pretty quickly on my recovery costs. We'd like to see a little more detail on that. Please don't show me 2 decimal places on anything ever in a conceptual or preliminary design. You showed me dollars and cents. Never, never, ever. So that means significant figures. You finished college, right? Any questions from you?
One thing. One thing that I would like to have seen, you start out the presentation saying these are the requirements. At the end of the presentation, or even in the beginning, show what the requirements were and how you met them all together.
Okay.
I was kind of having to jump between slides and pages to see, okay, what was the takeoff requirement? What was your weight requirement? That kind of thing. So
Okay.
that would have been nice to see.
Okay.
Slide, maybe it's on one slide.
All right.
Any questions from the audience? Here you go.
I just have one question about your configuration. How do you load your payload on the ground?
So working with Genesis, we know that we're going to have to load it within the hangar, wherever we are stationed out of. So it will be a mechanism to either lift the PT-1 to get it, because it's just a couple feet between and you will see their vertical stabilizer and the bottom of the PT-1. So it'll be to lift the PT-1 or to lower the ambassador and roll it underneath, and it will tract up.
Okay, thank you.